All right, let's start filling out our learning card for our least squared regression line. Now, the least squared regression line has some other names. Sometimes it's called the line of best fit or a linear model, or maybe it's called a regression equation. But we're going to call it the least squared regression line for this learning card. Well, what is it? Your line of best fit or your least squared regression line is the line that best represents the linear relationship between two quantitative variables. Another thing that we can say about the least squared regression line is that it minimizes the residuals. Now you may say, what is a residual? I don't know what that is. Well, a residual is the observed y value minus the predicted y value. One of the things that we should know is the predicted y value is predicted by your line of best fit or your least squared regression line. So if we look down here at this particular example, we've got temperature and clothing. So the temperature outside is going to determine the weight of the clothing that people wear. So as the temperature rises, people tend to wear less clothing. Therefore, we have a negative correlation or a negative association here. Now, what is the predicted value? Well, the predicted value for a least squared regression line is the value that is on the line itself. So this little purple dot is the predicted y. And this dot right here above it is the observed value of y. So the difference between the two, the observed y minus the predicted y, that is the residual. So this distance between those two right there, that is the residual. Now, what the least squared regression line does and what your technology usually does if you're using a calculator or a computer is it minimizes these residuals. That's why it's called the least squared regression line. So it minimizes these residuals. So now, how do I calculate the least squared regression line? There are actually three different ways to calculate your least squared regression line. One of them is to use your calculator or technology. Another one is to use a computer printout, but we're going to talk about that on a different learning card. But on this one, we're going to focus on how to calculate it using summary statistics and formulas. So if we have our summary statistics and formulas, how do we calculate the slope and the intercept to get our least squared regression line equation? First thing that we have to have are our summary statistics, and that's what we have right here. Our X bar, which is the mean temperature, is 62.4. Our Y bar, which is the average pounds of clothing, is 5.1. The standard deviation for X, which is the standard deviation of the temperatures, ends up being 31.9. And the standard deviation for Y, or the standard deviation of the clothing in pounds, is 4.2. The last piece of information, or the last statistic that we need, is R, our correlation coefficient. And you can see that R is negative 0.87. So it's negative, and that matches up with our scatter plot that has a negative direction. And 0.87 is fairly strong, so I would say this was a strong negative association between these two variables. I would also say that it's linear as well. I don't see any curve to that, so I would say this is definitely linear. Well, once we have all of these summary statistics, we just plug these into our formulas. So let's take a look at the formulas right now. So here's the formula for slope. It's B sub 1 equals R, your correlation coefficient, times the standard deviation of Y over the standard deviation of X. And when we plug all of that in, what we find is that our slope, our correlation gets plugged in here, the two standard deviations here, and then our slope ends up being negative 0.115. And that does match up. It's a negative relationship here, so this slope should be negative. Now, the second thing we need to find is our intercept, our y-intercept. And the formula to find your y-intercept is right here. B sub 0 equals y bar, so the mean of your y's, in this case the mean of the clothing, minus the slope times the mean of your x's, which in this case is the mean temperature. So I went ahead and did the math, and I end up getting this. So when we plug everything in, y bar was 5.1 minus the slope times x bar, which is the mean temperature, 62.4, and I get 12.3 as the intercept. Now, how do we put this all together into our least squared regression line? Well, the equation follows this. Y hat, which is your predicted value, equals the intercept plus the slope times x. So when we plug everything in, what we get for our least squared regression equation is pounds hat, the hat needs to be there, equals 12.3 minus 0.115, the slope, times temperature. So there is the way to calculate our slope and intercept and put it into our equation for our least squared regression line. Now, how do we use this? Well, one thing that we can do is we can interpret the slope. And when we interpret the slope, in this case, what we would say is something like this. For every increase of 1 degree in temperature, which is our x variable, for every increase in x, in this case, to provide some context, for every increase of 1 degree in temperature, we predict that y, in other words, our pounds of clothing, will decrease by 0.115. Now, because this is a negative slope over here, that's why we have to say all of this. For every 1 degree temperature, let me start that over. For every increase of 1 degree in temperature, we predict that pounds of clothing will decrease by 0.115. Now, what about interpreting the y-intercept? Well, if we interpret the y-intercept, it would look something like this. If the temperature is 0 degrees, because the y-intercept is when the temperature is 0, so we're talking about right here. If the temperature is 0 degrees, then the pounds of clothing is predicted to be 12.3. So that's how we can interpret the y-intercept. Sometimes the y-intercept does not have meaning. In this case, it does. The temperature is, it is possible that the temperature could be 0 degrees, but in some cases, it's impossible for your explanatory variable to be 0. So for example, if I was looking at a person's height compared to their weight, well, I wouldn't want to say, to interpret the y-intercept, if a person's height is 0 inches, then their weight is whatever. Well, if a person is 0 inches tall, then they don't exist. So sometimes the y-intercept has meaning, like it does in this example with the temperature and the clothing, and sometimes it does not have meaning. And if you were asked to interpret the y-intercept and it doesn't have meaning, then you would just say it doesn't have meaning because, and using my example, a person cannot have a height of 0 inches. Now, the last thing that we can do with the least squared regression line is we can make predictions. So if I were to plug in 50 degrees into my formula, I shouldn't say formula, but into my least squared regression equation for temperature, I could then do the math. 0.115 times 50 and then 12.3 minus that product is 6.6. So my prediction would be this. If the temperature is 50 degrees, then we can predict a person to wear 6.6 pounds of clothing. So going over everything, what is it? The line of best fit represents the linear relationship between two quantitative variables. How do I calculate it? Well, with summary statistics and the formulas, I calculate it like this. How do I write it? That's right here. This is the way that it would look. And then how do I use it? I can interpret the slope, interpret the y-intercept, and then make predictions. So there's our learning card for least squared regression lines, and I hope you have fun in your math class and your stats class.